Hello everybody. Welcome to Chapter 1, Chemistry 111. And this is where we actually get to start talking about chemistry. Up to this point, we've talked about the math skills you're going to need, and now we're going to talk real chemistry. So, chemistry is the study of matter. Composition, structure, the changes it undergoes, as well as the energy transfers and transformations when changes happen. So, we're going to be studying matter. What is matter? Matter is stuff. It's anything that has mass and volume. So when we talk about matter, we talk about matter being particulate in nature, which means it's coming in hunks. It's composed of particles. Okay, a particle is a hunk, no matter how small. The composition and structure of these particles determine the property of that type of matter. Okay? Now, we're going to use the terms atoms and molecules. Atoms, we'll hit on this more heavily, believe me, but first glance, atoms are the smallest pieces of matter to have both unique chemical and physical properties. Okay? Molecules are a combination of two or more atoms in a specific geometric arrangement relative to each other and with a specific ratio of one atom to another. Okay? Now, as we're starting to break down the definition of chemistry, one of the things that we need to understand about matter, okay, is its state. So what we mean by state, when we're talking about the state of matter, we're talking about the relative position of the particles one to another and the strength of the interactions between them. Okay? States of matter can change as we change temperature, which is submicroscopic kinetic energy, previews of coming attractions. Okay? And then we're going to talk about composition, which is a listing of the types of atoms present. Structure tells us how these atoms are connected, what order they're connected, and how they're connected. So, let's start breaking it down even more. Let's talk about the states of matter. The three most common states of matter found on Earth are solids, liquids, and gases. These are not the only states out there, but these are the three that are most common, and they'll be the ones we deal with here in Gen Chem. So, solids are when the particles are packed tightly together so that we have something that is rigid and has a set volume and a set shape. Okay? Liquids are still closely packed, but they're not so tightly packed that they can't move relative one to another. You can think about particles in a liquid as slipping and sliding past each other. They want to touch each other as they're moving along, whee, but they're going to move, okay? Whereas solids have a set shape and a set volume, liquids only have a set volume. They take their shape from their container. Whereas a solid is going to have multiple surfaces. We talk about a liquid having one exposed surface. So if you pour water into a glass, it only fills it up so far based on its volume, and then it's got a surface. Okay? Gases. No set shape, no set volume. The particles are really far apart. I mean, they can't see the other one from here. And there's lots and 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 lots of motion. Okay, so the particles are in constant motion. Here, the attractions between the particles are very weak compared to collision forces when they hit each other and they push apart. So, solids and liquids are not really compressible, which means you can't squeeze them down into a smaller volume. Gases are very compressible. They can easily be squeezed down into a smaller volume. So let's kind of look at this pictorially. Okay, here's some nice pictures to represent things. So you can see here in the solid, even when I put it in this container, it maintains, each piece of it maintains its shape. So the particles are tightly packed and they have a set shape and a set volume. Even if I go down to a grain of sand is a solid and it's an individual hunk of sand. Okay? Liquid, notice that it fills the container up to its volume. The particles are not so tightly packed and they're not as orderly. Okay? They're closely packed, but they're moving. Now, if we think about solid, well, I'll talk about that later. Gases. Okay? The particles are widely spaced. In fact, this is not showing how widely spaced they are. They're much further apart than this. They fill the entire container. There is no surface. So they don't have a set volume and they don't have a set shape. Okay, so solids, liquids, gases. Okay? When we see a change from one state of matter into another state of matter, we call this a physical change, because you have a change in appearance without a change in composition. Remember, composition is the makeup of the particle. Okay? It's composition. So if there's a fixed ratio by mass, so the ratio of hydrogen and the oxygen is the same in water if it's in the solid state, liquid state, and the gaseous state. So changing from the solid state to liquid state or liquid state to gaseous state would be a physical change. Okay? Now, besides changes in state being physical changes, there are other physical changes. If you were to cut a 2x4 in half, or fold a piece of paper, or rip a piece of paper, cut a piece of cloth. Those are physical changes. Okay? So we recognize a physical change by the fact that we have the same substance after the physical change that we had before. It just looks different. So ask yourself, do I have the same substance? If you do, it was a physical change. Okay? Now, physical properties. Physical properties are properties of the substance that you can see or say about it without it interacting with other substances. Okay? And it's in the observation you maintain the composition. So color is a physical property. State of matter is a physical property. The temperature at which physical changes happen are physical properties. Melting point, boiling point, the mass, the length of something, the height of something, the texture could all be considered a physical property. Now, if you do something with a substance and afterwards you don't have the same substance, then what you've accomplished is a chemical change. A chemical change is a change in composition so that the ratio of atoms changes, and what you end up with is different than what you started with. It's going to have a different set of physical properties. It will also have a different set of chemical properties, but you'll probably recognize the physical properties. Those will be obvious. So you know when you burned a piece of wood outside that what you get is ash. And ash doesn't look anything like the word you started with. So that's a chemical change. But if I took a piece of wood and I took an axe to it and I chopped it up, I just have smaller pieces of wood. That would be a physical change. Now, a chemical change, okay, is accomplished through a chemical reaction. Okay? So, by definition, a chemical reaction, a chemical change, is a change in composition of the substance or substances. So I might take one substance and make two substances out of it. I might take 2 or 3 substances and make one substance out of it. But that would be a chemical change. So words like burning, keep scrolling up, and rusting, cooking is all chemical, okay? The type of reaction a substance undergoes can be used to help identify it, as well as its physical properties that it undergoes. So if we look at 7.1 and 7.2 on page 290, okay, those are some questions that you can look at. I'm going to let you do that on your own, but look at 7.1, 7.2 on page 290, and the quiz on page 309, look at Q2 and Q3. Okay, I'm going to let you do those on your own. Hint, it would be important. Now, before we get into types of particles in nature, I want us to talk about energy. Okay, energy plays a key role in any type of change. A physical change, a chemical change. So a change in state or a chemical reaction are always going to have energy associated with it. So let's talk about what energy is. Okay? Now, energy can be thought of as the currency of the universe. It's kind of like electronic money. You never see that electronic money. It's never put in your hand, but you know it's out there. Okay? So you can call energy the currency of the universe. That's not a very sciencey definition. So if we go sciencey, it's the ability to do work. Now, what does that mean? Work doesn't mean holding down a job when we're talking chemistry and physics, even biology. Work means that you have the ability to change something's speed through the application of a force. So I push on something and it starts moving faster, or I push on something and I slow it down. That's doing work, okay? Energy comes in many different forms. We can talk about electrical energy, nuclear energy. We can talk about radiant energy, okay? We're going to start out with two really broad categories. We're going to talk about potential energy and kinetic energy. Now, there's lots of different kinds of potential energy that we could talk about, so we're just going big headers. Potential energy is stored energy. It's energy due to position or arrangement. Guys, what does position or arrangement mean? Well, here I have an eraser. Because I'm holding the eraser above the floor, we all know that if I let go of it, it's going to fall. Okay? So because of its position, it has potential energy. Potential for gravity, well, gravity's already pulling on it, but when I let go, gravity takes over and pulls it down toward the ground and speeds it up. So the stored energy, because I lifted it up, can be released as it goes back down, or converted as it goes back down into kinetic energy. When it hits the floor, it transfers that energy. Okay? Now, kinetic energy is energy something possesses because it's moving. So, if I have something moving, okay, and you can try this at home, set up a used bottle or can, something you can roll a ball at. When the ball hits them, boom, they move, okay? This is kinetic energy. Kinetic energy, because something moving, it can bump into something else and make that something move. Types of energy can be interconverted from one into another, like the potential energy of the eraser being converted into kinetic energy as it moves toward the floor. Or energy can be transferred. It can move from one object to another. Drop a hot rock into cold water, the water warms up some and the rock cools down some. Okay? When energy is converted from one form to another, or transferred from one object to another, we say that energy is conserved, which means the total amount of energy doesn't change. It may change type of energy, it may change who's got the energy, but the energy is conserved. Okay? When we're looking at chemical processes, Situations where we have lower potential energies are more stable and favorable than those with higher potential energies. So when we think about things happening, okay, if they're going to happen kind of on their own, spontaneously, we're looking at processes always moving from higher potential energy to lower potential energy. We can force things to go the other way, to go from lower potential energy to higher potential energy. But nature has a tendency to want to move toward lower potential energy. Okay? Now, energy is a hard concept because we can't really see energy. We see only the effects of energy transfers and transformations. So if this seems a little bit strange and alien, you're right, it is. It's probably something you've never really had to think about before. Now, we're going to look at energy first, flowing from one thing to another thing, or more precisely, we're going to talk about system and environment, or sometimes it's called surrounding. So let's talk about what a system is. A system is some small piece of the universe, like a reaction in the beaker, okay, or an ice cube, or a piece of paper, or a log. You could be a system, okay? The environment or surroundings is everything not in the system. So the lights in the room, the tabletops, the other people in the room, their environment. Okay? Now, the first law of thermodynamics states that the total energy of the universe is constant. And that means any energy lost by a system must be gained by the environment, or vice versa. If the system gained energy, the environment had to lose. Okay? Now, the units of energy in the metric system is the joule. We'll use the joule quite a bit in here. In the English system, it's the calorie. That's the one you are most used to hearing about. We don't really use that in chemistry, but I just wanted you to know it's out there. Okay? So for us, the system is really what we concentrate on. We're worried about whether the system is gaining energy or losing energy, or whether energy inside the system is being transformed from one form to another. Okay? The energy inside the system could have multiple forms. Okay? It can have potential energy, it can have kinetic energy, large scale, or it could have atomic scale potential and kinetic energy. Atomic scale we call submicroscopic because it's on the scale that's so small you can't see it with your eyes. Okay? The grand sum of the large scale potential and kinetic energy and the atomic levels potential and kinetic energy is called the internal energy of the system. Okay? ESYS. For us, large-scale potential energy and kinetic energy is not important. You usually do not hurl your chemical reactions across the room. And if you do, that's a no-no in lab. So we're not looking at large-scale potential energy and kinetic energy. We're going to concentrate in on that submicroscopic atomic levels. Okay? So, thinking about how we're going to look at the internal energy of the system, one of the things that we can run into as a roadblock is that it's really hard to get the total internal energy of the system. It's just hard to measure, it's hard to get at, and for us, that's not too big a stumbling block because we're really interested more in change in energy of the system, not the absolute energy inside the system. So we're going to look at energy flowing in and flowing out. When we look at energy flowing in and out of the system, we're going to talk about work and heat. Okay? Now, when I talk about work, remember I told you earlier, was the ability to apply a force and cause something to change motional state. Work is considered a large-scale process. It's a macro process. Okay? So work is not super common in chemistry. Now, when you move on to doing combustion engines, let's say in physics, or you're playing with dynamite, work would be a major way that energy would be leaving your system. I am not going to let you blow up dynamite in the lab. Okay? So we're going to very rarely see any work done. And if we do, it'll be by accident. Okay? The other form of energy that can flow in and out of the system is heat. Now, heat is an atomic level energy transfer. Heat is due to collisions between individual particles on that submicroscopic scale. So if you put your hand on a tabletop, okay, you'll feel the tabletop and it'll feel cool to your touch, or it should. And that's because your skin registers the direction of energy flow, heat flow, and the particles on average in the surface of your skin are moving more than the particles in the table. So that's heat. Okay? So if we're looking at changing the energy of the system, delta E of the system is going to equal heat plus work. Okay? Just to reiterate, in chemistry, work is not the main way that we see energy moving in and out of the system. Okay? It's going to be heat. Now, if we look at our equation, okay, let me scoot over here so we can look at the board for a sec. If we have delta E of the system is equal to Q plus W. And I'm down a few lights, a little brighter. If Q is positive, then the change in energy of the system is positive. And if Q is negative, delta E of the system is negative. So Q positive means flow in. Q negative is flow out. So a positive means energy is flowing in. I get a positive change in energy of the system. Energy flowing out, Q is negative. Same goes for W. If we had work, positive is for in, negative is for out. Okay? So energy in, energy out. Now, determining work for a chemical system can be pretty hard if we even have one that has work. So we're going to, instead of looking at this equation and trying to get Q and W both, we're going to look at something called enthalpy. Okay, so let's talk about enthalpy for a minute. Now, I'm going to talk about enthalpy all the time. Okay? Enthalpy is given the symbol H. And we use enthalpy instead of total internal energy of the system because enthalpy is going to be easier to measure. Okay? And just like with energy of the system, we're more interested in change in enthalpy, delta H, instead of change in internal energy. Okay? So let's look at things here for a minute. H is equal to E of the system plus P delta V. Now, if we go into looking at change, delta means change. Change in enthalpy then is change in energy of the system. I forgot my little subscript, don't worry. It should be there. Change in pressure times volume. Most of the time we're doing things in open containers. If we're doing things in open containers, we're dealing with constant pressure over our reaction. So pressure is constant, I get delta H equals delta E plus P delta V. Now, let me draw a pretty picture for you because this is where the magic happens. Okay? And don't panic. You're gonna go, this all seems so alien. It is. That's okay. Okay, here's a piston. Now, I'm gonna put some gas molecules here in my piston. They're screaming around, moving all over the place. Sometimes they hit the piston. the inside of the piston, and there are gas particles out here that are also pushing on the piston. Okay? If the piston's not moving, these guys are in balance with each other. The push on the inside and the push on the outside are the same. If this sucker moves out, so if the piston moves out to here, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. To expand out, in the process of going from here to here, these particles had to be hitting this piston wall of this piston harder than my green ones out here to move it out. And it'll move it out until they equal each other again. Okay? So here we can see that our delta V was positive. Okay? Now when our delta V is positive, that means that the gas inside here was able to push the gas outside out of the way. So this would be work out. So work here is negative. Okay? Turns out that when we're talking about PV work, work equals a minus P delta V when this external pressure is constant. Whee! Okay? Work is equal to minus P delta V. Now, what does that do for me? Well, we know that delta H for our system is equal to delta E for the system plus P delta V for the system. Okay? Now I'm going to play math games, guys. So delta H of the system is equal to Q plus W plus P delta V. Because anytime I change the energy of the system, I do it through work or heat. Work is minus P delta V when I'm under conditions of constant pressure. And notice I have a minus P delta V and a P delta V. They're going to cancel each other out. Delta H of the system is equal to Q. And I'm going to put a little P down here. P says under conditions of constant pressure. Okay? As long as the pressure is constant, then I can calculate the change in enthalpy of the system by looking at the heat flow in or out of the system. So delta H of the system is often referred to as the heat energy of the system, because we're basing it on Q under constant pressure conditions. Okay? So let's go back over to the screen. Okay, so that's what I've got for you here. Delta H is equal to Q sub P. So the change in enthalpy is equal to the change in heat, or the heat flow in or out of the system if we have an open beaker reaction. For most systems that we're interested in, okay, there is no work done. Work will always be 0, and there is no change in volume. If delta V is 0, then change in energy of the system is equal to delta H of the system. So we have a sneaky way of getting change in energy of the system without having to worry too much. Okay? So we measure heat energy flowing in and out of the system by way of temperature changes. So let's talk temperature. Temperature is a measure of how hot or how cold something is. To be more precise, temperature is a measure of average kinetic energy of the particles that make up the system on the atomic level. So remember, kinetic energy is energy something has because it's moving. So we can talk about translational motion, we can talk about rotational motion, and we can talk about vibrational motion. All of those contribute to that atomic level kinetic energy. Okay? So we're going to look at energy flowing in and out of our system by way of interactions on that atomic level, and we're going to be able to track it by way of temperature. When heat flows in or out of the system, there's going to be a temperature change. Okay? If the temperature goes up for our system, that means the system gained energy. If the temperature goes down for the system loses energy. Now guys, we got to be really careful about knowing what we're measuring the temperature of here when we're looking at whether our system is gaining or losing energy. Okay? So let's talk about the terms exothermic and endothermic. An exothermic process means that the system is losing heat energy. Endo means that the system is gaining heat energy. Okay? So if I were to take a 100-degree rock and put it in a cup of water at 20 degrees C, the rock would give up heat energy to the water. So the temperature of the rock would decrease, the temperature of the water would increase. So that would tell me who was losing energy and who was gaining energy. Interesting enough, they'll do this until the two end up at the same temperature. Okay? Which means they have the same average kinetic energy. So for the rock, it's exothermic. For the water, it's endothermic. Now, the transfer of energy stops when they both reach the same temperature. They don't stop trading energy, but for the amount of energy lost by the rock to the water, there's energy gained by the rock from the water. I know, it seems wild, but that's what happens. Okay? When a chemical process, a chemical reaction is going on inside a beaker of water, the water is part of the environment. It's not part of the reaction. And what we usually do in that situation is we're going to be measuring the temperature change for the water. Okay? So if I had a reaction going on and I had a thermometer stuck into the water that the reaction was happening in, and the temperature of the water goes up, that means that it gained energy from the reaction, which means that the chemical reaction is exothermic. Okay? So, at the chemical level, at the atomic level, bonds are being broken and bonds are being made when a chemical reaction is happening. Okay? When new bonds are made, energy is released. It's exothermic. When old bonds are broken, it's endothermic. So when you're making and breaking bonds, if you make stronger, better bonds than you had in the beginning, you're going to end up with an overall exothermic process. If it takes more energy to break bonds than you get when new bonds are formed, you get an overall endothermic process. So if the overall process of making and breaking bonds is endothermic, then the water in the beaker increases in temperature because energy is flowing out of the reaction and into the environment and being caught by the water. Okay? If the overall process of making and breaking bonds is endothermic, then the water in the beaker actually experiences a decrease in temperature. Because energy is being sucked out of the water and into the components of the reaction. Okay, now let's think about atomic level potential energy and kinetic energy here for a minute. Okay? Potential energy and kinetic energy at the atomic level are being changed when a chemical reaction is going on. So there is a interconversion from potential energy to kinetic energy inside the components of the reaction, or there's a change from kinetic energy to potential energy inside the system. And remember that energy has to come from somewhere and go to somewhere. So for an exothermic reaction taking place in water, let's kind of step through what's going on with the energy. Potential energy that is stored in weak bonds is converted to kinetic energy inside the system as strong bonds are made. Which means that kinetic energy means that those particles are moving faster and they're going to bump into the water molecules they're floating in, and they're going to transfer energy out to the water. And we see an increase in the temperature of the beaker. So energy is flowing over time out of the beaker into the room. This is an exothermic process. So anytime we observe an increase in temperature when we have a reaction in a beaker, it's exothermic. Now, endothermic. Kinetic energy in the system is converted to potential energy inside the system. So I took something that had strong bonds and I made something that had weaker bonds out of it. To do this, it pulls energy from the water that's in the beaker. And you see this as a decrease in temperature of the water. And slowly over time, then the water will start pulling energy from the room until it gets back to its original temperature. So in an endothermic process, energy flows into the system. It's used to break strong bonds and to make weak bonds, and that stores it as potential energy. Hint, we store energy in weak bonds. Okay? So an exothermic reaction happening in a beaker is going to feel hot to the touch. An endothermic reaction happening in a beaker is going to feel cold to the touch. Okay, because your fingers register the direction of heat flow in and out of the body. All right. So think about a hand warmer or a cold pack. Since we're not in class, I can't show you my reversible hand warmers, but some of these things can be reversed. Okay, you can read through that, and we'll worry about that later. So let's talk temperature for a minute. Okay, temperature is a measure, of course, of how hot or how cold something is. But what does that mean? Okay, temperature, in a more sciencey way, is the measure of the average kinetic energy on the submicroscopic level. It's the sum total of it's based on the kinetic energy of the system, also referred to as the thermal energy of the system. And it's measured, remember, it's related to average kinetic energy. Therefore, it's possible for two objects to have different total thermal energy contents because they're different size samples and have the same average thermal energy content and have the same temperature. So a 100 gram sample of water at 100 degrees C and a 500 gram sample of water at 100 degrees C both have the same average kinetic energy, but they have different total energy contents. Okay? Now, the temperature scale you're most familiar with is the Fahrenheit scale. I hate to tell you, we don't use that in chemistry. We're either going to use the Celsius scale or the Kelvin scale. Now let's look at temperature conversions. Temperature in Kelvin equals temperature in degrees C plus 273.15. I expect you to be able to use that. It's an easy one to memorize, but if you don't panic. Here's the relationship between temperature in Celsius and temperature in Fahrenheit. Temperature in Celsius equals 5 nights times the temperature in Fahrenheit minus 32. Now, if I ask you to do this problem on a test, I will provide you with this equation. This is not one I expect you to be able to do from memory. You also might want to have that available when you're doing your online homework, because I think there are a couple of these conversions that pop up in there. I tried to avoid them, but sometimes they rotate things in because they do multiple versions of a question, so you could hit one of those in the homework. Okay? If the temperature of a sample changes, then we know energy had to flow in or out of the system. All chemical and physical changes comes with some kind of energy transfer in or out of the system. Okay? Doesn't matter. We're going to skip this part on calculating. We're going to do that second semester, so you can skip over this section on calorimetry. You can read through it if you want, but I'm not going to be testing you on this. Keep going. Keep going. Okay, let's switch gears. Okay? Now, we've talked about energy. Now we need to start looking at classifying matter. Talking about the types of particles and how we find particles out there in the real world. Now, remember, matter is anything that has mass or volume. One of the first questions we ask ourselves when we've got stuff, okay, is do I have one type of particle or do I have more than one type of particle? If you've got one type of particle, you've got what's considered to be a pure substance. If you have two or more types of particles, you have a mixture. Okay? Pure substances, we're going to talk about either being elements or compounds. If the one type of particle you have cannot be broken down into anything simpler by a chemical process, you've got an element. If the one type of particle you have can be broken down into things that are simpler in a chemical process, you've got a compound. Okay? If you have two or more types of particles and they're uniform throughout, which means that if I took one spoonful and the next spoonful and the next spoonful, they're all identical, you have something that's homogeneous. If they're not, heterogeneous. Heterogeneous is like taking spoonfuls of chicken noodle soup. Homogeneous is like a cup of tea. Okay? Now, if we look here, okay, looking at our pictorial representation, and don't worry, we're going to be hitting this in more detail. Notice here I have helium particles. They're helium atoms. Individual atoms, they're all identical to each other. Okay, so I have one type of atom, one marble, okay, universe of small marbles, and they're all identical. Here, I have water molecules. I still have only one type of particle, but it's made up of three atoms that are fused together. We have two hydrogens and one oxygen. So this could be broken up into individual marbles. Okay? It can be split smaller. Now here in our tea, we have water and caffeine and sugar. Okay? They're all hanging out together, but they're individual particles. We talk about this being physically intermingled. Okay? They're out the party together, but they can all walk away from each other, spread out. And they're nice and evenly distributed. Now, I'm not real fond of this one as an image because it makes them look like they're totally separate. Okay? But you can see I have sand particles here, I have water particles here. They're tumbling around in that tumble of water. But think more chicken noodle soup, where you can see a chunk of carrot and you can see the chunks of chicken and you can see the noodles. Every time you get a spoon, you get something different. Okay? So let's dig a little deeper. So let's talk it through. Pure substance is made up of one and only one type of particle. It has a fixed composition and it does not vary from one sample to another. Pure substances can either be elements or compounds. An element is a substance that can't be chemically broken down into anything simpler. Okay? Scroll up. The smallest piece of an element to have all the properties of an element is an atom. You can find molecules of elements, and when we start encountering those, I'll point them out to you. Remember, a molecule is a combination of two or more atoms that are chemically bonded together. So they could be identical atoms, or they could be atoms of two different substances. Now, a compound is a substance composed of two or more elements in a fixed defined proportion. Okay? The properties of compound are different from those of the elements they're made of. And in nature, we see a lot more compounds than pure elements. Pure elements are hard to find. You can find some sulfur deposits around volcanoes. Of course, we mine gold, and we can find a gold nugget that is pure. You can mine silver. I don't think there are really any good pure copper mines left. They were kind of mined out in antiquity. But very few things we encounter are pure elements if we find them in nature. Okay? And the reason for this is energetically, energy, having compounds is more favorable, has a lower potential energy than most pure elements. The smallest piece of a compound to have all the properties of the compound is the molecule. When we talk about ionic compounds, I'm going to refine that a little bit because ionic compounds are a little weird. Molecules. Okay, just a reminder, it's a combination of two or more atoms bonded together. You have molecules of an element, you have molecules of a compound. A mixture is a substance composed of two or more types of particles in portions that can vary, and the particles are physically intermingled. That means they're not super glued, they're not handcuffed together, they're just casually hanging out. Okay? So, a mixture can have a varying composition. If you make fruit salad using pineapples and mandarin oranges and marshmallows and sour cream, it's one of my mom's favorites. The ratio of pineapple and mandarin orange and sour cream always varies when my mother makes it. But it's the same salad, it's got the same three components, it's just a little different every time. What can I say? My mom was a child of the 50s.